to adjust the pointer to 0 scale. Let me say it again. The hot wire emitter is provided with an adjustment screw to adjust the pointer to 0 scale. Why? Give reason. Okay, the resistance wire, the wire which is made of platinum iridium, is affected by changes of the atmospheric temperature of the surroundings. When the resistance wire is affected by the temperature of the surroundings, okay, it expands or shrinks, so its pointer moves away. It moves away, okay, from 0 scale. From the 0 scale, and hence it requires adjustment before using it. So each time you use it, you have to adjust the pointer to 0 scale, okay? Another give reason. The resistance wire of the hot wire emitter is stretched over, is mounted over a plate made of a material that has the same coefficient of expansion as the wire. I'll say it again. The resistance wire of the hot wire emitter is stretched over a plate made of a material that has the same coefficient of expansion as the resistance wire. This is to eliminate, to cancel out the effect of the atmospheric temperature of the surroundings. We do this. We place the resistance wire, okay, on a plate made of a material that has the same coefficient of expansion to eliminate the effect of the atmospheric temperature. In this way, the wire is kept taut and the plate will expand by the same amount as the wire. We want you to compare between moving coil galvanometer and hot wire emitter. Idea of the moving coil galvanometer, or the function of the moving coil galvanometer, is based on the magnetic effect of the electric current. But hot wire emitter is based on the thermal effect. Moving coil based on magnetic effect, magnetic torque. Hot wire emitter is based on thermal effect. Okay, and what about the second point of difference? Moving coil galvanometer measures only. It can be used to measure only DC currents. It cannot be used for measuring AC currents. But hot wire emitter can measure AC and DC currents. It measures the effective value of the AC current and it measures DC currents. Scale of the moving coil galvanometer is uniform. Theta is proportional to the current. But scale of the hot wire emitter is not uniform, simply because theta is proportional to I squared, not to the I itself. The pointer of the device, pointer of the moving coil galvanometer, stops, okay, stops moving when the electromagnetic couple, is the couple produced when the current required to be measured is passed through the device. The pointer stops when electromagnetic couple is balanced by mechanical couple. But the pointer of the hot wire emitter stops moving when the resistance wire reaches the temperature at which the heat produced in the wire due to the flow of the current equals the heat lost by convection. Moving coil galvanometer has high sensitivity. Hot wire emitter has much lower sensitivity. And now, talking about disadvantages of each one of them, talking about the moving coil galvanometer, as time goes on, as time elapses, the hair springs become inactive, they slacken away, and the magnet loses some of its strength. So the device requires to be recalibrated, requires recalibration from time to time. This was about the moving coil galvanometer. And disadvantages of the hot wire emitter, as we said, its sensitivity is small, is low. Also, there is a disadvantage for the moving coil. It only measures DC currents. It cannot measure, AC currents. Disadvantage of hot wire emitter, yes, it is affected by the temperature of the surroundings, atmospheric temperature. The pointer takes longer time to measure the current and to return to zero, so it takes time to measure, and it takes time to return to zero when it is disconnected after finishing measuring the current. What happens when? Another type of questions. What happens when switch in the opposite circuit is opened? The circuit shown. Account for your answer. The circuit is shown right now. When the switch is opened, the lamp, thank you very much, momentarily flashes due to the high forward EMF induced by self-induction. This is very important experiment. Usually we use it or we perform it to demonstrate self-induction. So, when the switch is opened, the lamp flashes due to, the high EMF induced by self-induction. And it is, of course, forward since we opened the switch. What happens when the two metallic rings in an AC dynamo are replaced with a split cylinder commutator? Okay, the AC current becomes unidirectional varying current. It is shown in front of you. AC current becomes unidirectional, having, same direction, but still varying. Okay. What happens when the value of R1 is decreased with respect to the readings on the voltmeters? Okay. So in front of you we've got a circuit. Value of R1 is decreased. And we want you to explain what would happen to the readings on V1 and V2. Okay, we want to explain this. V1, reading of voltmeter 1. Okay, what about it? It is the terminal voltage. And V2 is the voltage just across R2. V1 is the voltage across R1 and R2. Okay, so V1 decreases but V2 increases. Why? I'll explain this. When R1 is decreased, total resistance of the circuit decreases. Thank you. And the current increases. Okay, when the current increases, lost voltage, IR small, increases. So terminal voltage, external voltage decreases. Terminal voltage is V1. V1 decreases. V2 depends on the current simply because it is the product of IR2. R2 is constant, so it depends on the current, and current, increases when resistance decreases. So V2 increases. Okay. Once again, decreasing the value of the variable resistance decreases the total resistance of the circuit, causes the total resistance of the circuit to decrease. So the current passing through the battery increases. And this causes the internal voltage, we call it lost voltage, and it is determined by the product IR small. Okay, when current increases, internal voltage increases, and terminal voltage V1 decreases. And what about V2? As I said, it increases because it is proportional to the current. Another type of questions: when does each of the following quantities equal 0? When does each of the following quantities equal 0? Okay, when does the torque acting on a coil carrying an electric current and placed in a uniform magnetic field, yes, equal 0? In the vertical position, thank you very much, the torque equals 0 in the vertical position, where the plane of the coil is perpendicular to the magnetic field, perpendicular to the field lines in the vertical position. Torque is determined from the equation BIA and cosine theta. B, magnetic flux density. I, current intensity. A, face area of the coil. Turns on the coil. Cosine theta. Theta is the angle between plane of the coil and magnetic field. So in the vertical position, plane makes an angle 90 with the field, and cosine 90 is equal to 0. When does the EMF induced in a wire moving in a uniform magnetic field equal 0? Okay, when the wire is moved parallel to the field. So no cutting, so no EMF induced. Since EMF induced is equal to BLV sine theta, EMF induced or instantaneous EMF will be equal to 0 when theta equal 0. Theta, of course, as I said, is the angle between the field and direction of motion of the wire. So when the wire is moved parallel to the field, no EMF is induced in it. When does the force of a magnetic field on a current carrying wire is equal to 0? When does it equal 0? When the wire is placed parallel to the field, then the field will exert no force on it. Okay, the formula that gives the value of the force, F is equal to BIL sine theta. So the force is 0 or equals 0 when theta is 0. Sine 0 equals 0. When does the value of the instantaneous EMF induced in a coil rotating in a magnetic field equal 0? Of course, the instantaneous EMF equals 0 in the vertical position where the plane is perpendicular to the magnetic field. The sides do not cut the magnetic flux lines. So it happens when the coil is in the vertical position where the plane is perpendicular to the magnetic field. Okay, instantaneous EMF equals EMF maximum cosine alpha. So instantaneous will be 0 when alpha equals 90 in the vertical position. Alpha is the angle between plane of coil and magnetic field. When does the current flows through a primary coil of a transformer equals 0, though its secondary is connected, so its primary is connected to the supply. Okay, we've got a primary, we've got a transformer. The primary coil is connected to the supply. Okay, but no current flows through it. It happens when the secondary coil is unloaded, that is to say the secondary circuit is open. Okay, and now let's solve a problem. Okay, we've got two wires which are mutually perpendicular and a point which is 20 centimeters from wire carrying 2 amperes and 10 centimeters from wire Y which carries 1 ampere. We want you to calculate the total magnetic flux at point Q. At point Q, two fields, okay, reach this point. So at point Q, the magnetic flux density due to wire X equals 2 times 10 to the power of negative 7. Current passing through wire X, which is 2 amperes, over the distance of the point Q from the wire, it is 20 centimeters, so times 10 to the power of negative 2. The field is equal to 2 times 10 to the power of negative 6 Tesla. This is the field due to X. We'll obtain the field due to Y. We'll do the same. Field density due to wire Y, 2 times 10 power negative 7. Current flowing through the wire Y is 1 ampere. Distance is 10 centimeter, 10 to the power of negative 2. And it is equal also 2 times 10 power negative 6. So total field at point Q will be the difference, so it will be 0. And now we've got very important question. A student disconnects the voltmeter shown in the circuit in front of you and connects in its place a battery and a switch. But when he closes the switch, the coil does not rotate as it should in a DC motor. Okay. What is the reason for this? And what is the other change will he has to make before the motor works properly? Okay. First of all, when he closes the circuit, the coil will not rotate in one direction because of the presence of 2 rings. We have 2 rings. The 2 rings, okay, the 2 rings of the coil reverse the direction of rotation twice a cycle. So the change here is to replace the 2 rings by split ring commutator. The split ring commutator reverses the direction of the current in the coil each half cycle to make it rotate in one direction. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank